Good evening. So this is part 5, I guess, of this exercise of doing a vectorized virtual machine for computing activation functions. So just to get you situated, we are working on tract, which is a neural network inference engine. And the part of executing neural network is computing very fast. And one of the things that we have to compute is activation function on a bunch of data, on entire tensors. So these activation functions are just functions that do not use the geometry of the tensor. So you can see the tensor are just a big slice of numbers, and we need to apply the same transformation, the same computation to each and every element in the tensor. And as we must compute many of them at the same time, and as they are independent from each other, basically the idea is to make it as vector friendly as possible with the CPU, so we can get the best performance possible. So so far we've written a lot of Rust doing so. So we started by making kind of inventory of the function, the activation function that we wanted to implement. So some of them are really simple, like Relu, which is just a max with 0. There is better, easier to understand expression here. Some of them are a bit more complicated, like this one or even the out switch. It's not that complicated, it stopped there. This is just nota bene about the two constants. We have designed a small virtual machine that is basically designed by example here. So we have some operations that so we have registers. We find out that we can do everything we want with 3 registers apparently. And so we have a couple of operations that we need to represent all of these computations. And these operations, we've moved them around last week. So let me get the right branch. Activation VM. So lineal is a creating tract that deals with high performance computation. And what we've done is in frame, we have started working on this activations problem. And if I go back one time, here we have our 3 registers. This is the instruction list that we figure out we need to implement all of these computations. This is a structure that contains a program which is made of several of these operations and a couple of constants that are used in the computation. And ultimately we have an implementation. So it's not living here. No. So we don't have the implementation here. We have a couple of traits which I described last week, which are part of tract and which allow us to have several implementation of the actual computation wrapped behind the same interface, so that we can switch the actual implementation depending on the machine we're running on, and to get the best performance from the architecture. So that's what's in frame. So frame is everything Rust, meaning this part will be run whatever backend we use for the computation. So if we're using handcrafted assembly backend, we will still be using this part to go from the high-level interface to the assembly interface that we will have to implement for the specific backend. And beside that, we have in generic, we have one of these backends which is written in Rust, which we took from our earlier experimentations. And this this represents the computation that we have to mimic in assembly to compute all of these functions. So there are quite a bit of them, but we'll start slowly, because we don't need all of them to start observing stuff. And this is what plugs the compute slice function up there into the right trait, so that can be picked up by the other traits that were in frame. Okay, so I've been teasing the assembly thing for a while now. It's not that, getting there took a bit of time, but I think now it's really time that I start making a fool of myself and try doing assembly in a live coding session. So let's try it. The good thing is it's not my first time, and we have a lot of things that we can use in tract linalg, because all the matrix multiplication stuff is also implemented exactly in the same spirit. So we have Rust frame layer, and below that we have generic implementation in Rust, and you have specific implementation in assembly for each platform or architecture that we want to target. So basically we're just going to mimic this. So the first thing we are going to do is we're going to define a function that will be our backend in assembly. So we will put it in this directory. So we have various of ARM64 variant that we can address. So the most generic one is this one. So basically all ARM64 chips have this advanced SIMD support, which is basically what was called Neon on ARM32. It's not too hard to work with, so we will start with this one. And so we'll do a file that we will call ARM64 SIMD, and we'll use act for activation. And what else do I need? ARM64 SIMD. So I'm taking inspiration here. So yes, I'm going to work on F32. And so the next parameter, the 4n, if I look at previous implementation of sigmoid and hyperbolic tangent, these 4n are an easy code. I mean, a reminder of what kind of geometry the function can support. And the 4n means that we expect the slice to be operated on to be of size to contain 4 F32 or a multiple of 4 F32. So it could be 4, it could be 16, it could be 128, but it cannot be 5. We want to operate on a strict multiple of our window. We don't want to deal with borders. This is what the Rust frame part is doing for us. So the question is, how many operators will we, how many items will be operating it? We will be treating in one single pass. So let's try to figure this out. On ARM64, we have 32 general purpose registers that we will, we will not use all of them. We will use some of them to do some housekeeping, but we will not use them for computation. And we have 32 128 bits vector registers. which are the SIMD registers. And what we are going to do today is we are going to use this one as 4 F32 vectors. So now on the other side, on this side of what we were designing, we need 3 registers, A, B, and C. And we need some more room for housekeeping. Let's just be vague. And the idea is each of these 3 registers will span several of these SIMD registers. So I think what we can do is one activation register maps to 8 SIMD vectors. So the SIMD vectors are V0. I mean, there are several ways to call them, but the most common one is V0 to V31. So here we say that A will be V0 to V8 included. So yeah, okay. I'm not gonna use the Rust syntax, but more math syntax. So this is inclusive, or I could just write it. Yeah, V0 to V31 and so A will be V0 to V7 inclusive. B will be V8 to V15. C will be V16 to V23. And then we have V24 to V31 inclusive for housekeeping. Okay, so this is the main idea. So the consequence of this is A contains 8 each activation register maps to, oops, that's exactly what's written here. So that's 32 floats, which means that we will be operating on 32 values at the same time, or nearly at the same time. Okay, so consequence for here, the name of our function should be 32n. And I'm going to keep it like that for now. So I'm using the tmpl extension. There is some lag in my keyboard, I'm sorry about that. My typing will be a bit weird. I'm using the tmpl because the thing is, we are not writing assembly. We will be writing a template of an assembly file. In our case, I think I will try to stay away for many things too templatey, at least at the beginning, because I mean, it gets hairy, it gets complicated. But the point of the templating is to be able to adjust the assembly so that it will work on Android and on Linux, or work on Windows as well as on Linux and macOS, depending on what is the actual assembly that we will be using. So basically it's like a preprocessor, but the preprocessor also, I mean, usually the preprocessor is shipped with the assembly. So depending on your assembly, you need a different preprocessor, but what I want to do is to use one preprocessor for everywhere. So I picked Liquid, which is actually a preprocessor that makes web pages, but I mean, all of this is just text, so it works also for assembly. So next I'm gonna look at one of the I'm gonna cut and paste a lot of stuff again tonight. So I'm going for this one. So I have this reminder of which registers are preserved and which are not. That is useful to keep in mind. This, on the other hand, is about the actual kernel. So this is a matrix multiplication kernel. So what we are going to do is we're going to pick these lines up. Yes, good. So there is a bit of ceremony here, but this is essentially introducing the function name. So the function name will be, this is right, so this is act, and this is 32n. I don't have the core thing on this one, but keyboard is really doing weird stuff. Maybe if I plug it in actually. Sorry, I'm gonna make a bit of noise. Struggling with wires. But let's try like that, see if it's better. Hopefully I'm done with the noise. Okay, so a bit more of ceremony. So the G is because depending on the architecture, we need a prefix on global symbols. That's a G. That's what the G stands for, and it's set by the build script that we will be looking at very soon. And I need this. No, that's not a global. No, that's a label. Here we go. What the suffix is about, is about putting a different suffix on all of the functions that we are going to generate. The reason is if we have two versions of tract compiled in the same artifact, in the same Rust, in the same Rust product, we want to make sure that one of the functions from we want to differentiate the function, and we want each part of the Rust code to call the right part, the right assembly function, and not mix them together or have one over, taking over the other one, because if we change something in the way the Rust code and the assembly code should communicate, then it would break in absolutely terrible ways. So that's security. Once again, the suffix variable is provided by the build script that we'll be having a look, maybe right now. Before that, I'm going to do the register saving. So when you do assembly, there is something called the calling convention, which says how a function should call another function. And part of these calling conventions states, and that's the bit which is here. So that one is not our business actually. But here we have this bit that says which registers we have to preserve. The thing is, on the vector side of things, so we have the X registers. The X registers here are the general purpose registers, and these guys are the vector registers. And so there is a weird thing is we need to preserve, which means we need to preserve some of these registers. And what does that mean? It means that when we exit the function, we must restore them in the same state as they were when we enter the function. And this and so the weird thing with this architecture and with this coding convention is we just have to preserve half. For 8 of these registers, we have to preserve the lower half of each of them. So the V prefix designate the entire 128 registers, while the D prefix designates the lower half. So what these 4 lines are doing is for each of 8, 9, 10, 11, 12, 13, 14, and 15, they will push on the stack, which is in SP, the lower half of these of V8 and V9, V10 and V11, etc., etc. So that's so this is what we are going to do when we start this function, to make sure that we store somewhere the previous values that were in these registers. And of course, the point is, at the end, we will restore them. So this is exactly symmetrical. So this way, we at least ensure that we will not be breaking whatever was in these registers. Once again, this has to be done very carefully, because that's the kind of thing that will break in very subtle way, not all of the time, and so it can be a real pain when you miss one of these register saving things. It can be a real pain to actually find out what was the issue. So here I have a function with a name a bit complicated, but that will do. That does nothing except pushing on the stack 8 half vector registers, restore them at the right position, and return. And one thing that I want to do, which I do in the matrix multiplication kernel, so I'm going to do it the same way, is I want to use the return value as a hint to say that everything went fine, or if there was something wrong. And to do that, I think the actual code that I want to cut and paste is in dispatcher. So dispatcher is actually the dispatcher for the matrix multiplication. I will explain later why is it called dispatcher. And so that's what I'm looking at. I want to put a 0 in the first general purpose register, and I want to jump to return. This is a NOP because it's just after, but okay, I'm gonna just put it like that. And you can see here on the matrix multiplication code, when I have unsupported operations which are required, I use 1 as a return value. It's not super clear to me when the hash must be put in front of the constant, and I'm not super consistent with it, obviously. It's there, but it's not there, so I'm not sure. Okay, so this is a function that we can call from Rust, and that should just return 0 and do nothing else. But before we call it, we need to build it. And maybe there is nothing to do, because okay. Because I think I'm looking at all of the files with the tmpl extension and run the preprocessor on them before compiling assembling the assembly output. So this is arc64, that's what we are doing. So we are processing all of the files in ARM64 SIMD. Yes, I think that's all we have to do. This is for the M1 and M2 special magical stuff. This is for floating point, half precision floating point. That's for ARMv8.2. But for now we are staying with ARMv8 purely standard, so we want it everywhere, so we want to go through this code and it should work. This is for cases where we need to differentiate some part of the assembly depending on the specific cores. So we have specific stuff to deal with Cortex A53, to deal with Cortex A55, and the rest goes to Gen. For now we will consider that we are doing generic code and not optimizing for one of the two Cortex, which usually requires some more optimization. Even if we are going to be using a Cortex A53 for testing, that's fine. Okay, so I have some bit of assembly. I have a build.rs that should work, and what I need now is I just need to link this function in Rust code and somehow call it. So let's do this. And this happened in ARM64, and I guess that this one, nope. Okay, so ARM64, yes, ARM64 SIMD. Okay, here we go. So these are all the functions that we previously defined and that can do essentially matrix multiplication. So from here to, well, all of these are matrix multiplication for floating point numbers. These two are quantized numbers, so they're operating in integer and not in floating point stuff. These are the half precision floating point kernels. These are for computing hyperbolic tangent and sigmoid in single precision, same in half precision. And now we are going to add something else, and I don't remember if we did the underscore amp function, that macro that I wanted to do. I remember that I was hesitating about that, so let's check. So it should be in frame activations. Activations like this, maybe. So we have the trait, and yes, that's the one. Act implementation. So let's go for it. Act implementation. And what do we need? We need an identifier. So the identifier will be ARM. So it's a function name, really. So let's have a look because I forgot. ARM64, ARM64 SIMD, and ARM64 act. Yes, the first one, it will be convenient. So ARM64 SIMD act F32 32n plus suffix. So suffix doesn't need to be there. It's generated by the macro. Appended by the macro. And we need what we need. So we need NR. So NR is the number of elements that we want to process at one single time, and we need alignments in items. And what we are going to be using for loading data is instructions that I think require the values to be aligned on 128 bits. So exactly on the size of the vector, so it will be 4 F32. And that should do it. And the good thing is, if I remember correctly, No, we did not. So what I'm usually doing is I'm adding the tests to the macro so that I can, so that it's impossible to forget to plug in the test. So we will do that later on, I guess, because we will be wanting to test a lot of things anyway. So let's see if this compiles and links. So to compile, I'm going to use Dingy, which is a series of cargo helpers to cross-compile and cross-link to a different architecture. And I'm going to target Raspberry Pi. So this is known by Dingy. And let's say that first I want to build. Okay. So there is something wrong with my macro usage, I guess. 64, ARM64. So I put 64 and 4. Yes, I think I forgot. You can see that the other macros have the type actually at the left. I should probably align the convention so it's the same frame activations.rs. So TI, TI is the operating type, so that's what is missing. Let's try again. Okay, so this macro never, we did not use this macro because the way that the Rust is plugged in is a bit different from the way the assembly kernels are plugged in. So we did it without the macro. So that's the first time we actually debug the macro. But it's going to be all right. It's going to be fine. Op has to be create frame activation with an S. And activation care, actually, yes. And that's 111, just the same thing here. So create frame activations, activation kernel. Let's go. Okay, so not there yet. Expected slice found, yes, that's true. This is a slice. What else? That might be it actually. Nope. So, this function takes 2 arguments, but 4 were supplied. So, sysfunc should be my function here. So I need to fix, yes, I need to fix the prototype. So what did we decide last time? We decided that the kernel, so I can refer to the Rust one, which is in generic. And so the prototype is, yeah, it mimics this. So we have, it doesn't mimics at all, it's exactly this. Up, up. Okay, so I need to change F32 by, my keyboard is still misbehaving, it's crazy. like this. And let's see now. Op is not found. Okay, same story. I have a module here, so I can use it. Use create ops. Nope. Frame activations. Op. Okay, it compiles. It compiles unused macro definition, prop activation. So that's yeah, that's because we're not using. I mean, this is a test macro and we're not using it yet. So let's plug in the test right away, or maybe not yet. What I'm going to do first is I'm going to, because when I call build, we build library, but we're not building, we're not linking everything. I mean, it's not a final artifact. So there can still be missing symbols. So I'm just going to do this. So if I'm running test, Rust will actually have to generate executables. And this is where we will see if the symbol that we are expecting here has been properly instantiated and added to the binary by the build.rs. Even if the test will not learn us a lot, because we are going to just test stuff that already exists. So the computer that does the work and the Raspberry Pi are not in the same place, so the installing bit will always be a bit long. If it works at all, that is. I tried it before, so I hope it will be working. In the meantime, I can have a look at plugging in the actual test. So we did write some tests. So this is a simple test to check that our operation has a fixed size of 4, and the test is a separate file. Activation test. So what do we have here? We have these act frame tests, which are using this code, and I think what we want is we will want to augment these, because here we are testing I'm trying to figure out what this does, and actually no, it tests at relatively low level. It calls the run function of the kernel directly. I was wondering if this bit was testing the run function of the kernel or the frame function plus the kernel. So the tests are running, which means that the executable was built. So we are probably good to go on this, on the linking and building stuff. So here we are testing against the reference. I think I will want to do some simpler tests where we test not is affine working, but instead is addition, is multiplication working. I mean, each of the operation that we are going to implement. Okay, but let's try to do this, and I'm going to write the code directly, and then we will macroify it. Tests. config test. Okay. So what we want to do is, let's say we want to test that the first thing we will want to test is that an empty program returns 0 and doesn't alter the data that we provided. Let's test act nope, and we want to test this function, but actually what the macro does is this name in the Rust code is not a function. It's actually an object called. It's an object. The name is just this, and it implements the trait activation kernel. So we can use the trait directly. So for instance, if I do ARM64 32n.run like this, it would be nice if it were compiling, but I'm on the wrong architecture. I'm not on the right architecture. So this code, so the code that I'm editing is not compiled when I'm editing. So let's do it the other way around. We will work on the generic kernel instead. First, activations. So we've done act frame test, and we'll do repeat this, and we need to call so the kernel that exists, which is s activations, and so prog will be just up down, need to import up, and run will use prog constants. So the constants might end up being a pain, but let's try it like that. And we need x, let x equals, let's do something simple. So we will make it a vector of 1, not too fun. Yeah, vector of 1 repeated s activation n r times, because we can only call our kernel with the right number of items. I guess the problem is it doesn't know that. It doesn't know the trait. So I actually need s activations implements implement activation care. So I guess I need to use as a trait. Maybe it's bizarre that the VIM doesn't help me here. No, that's okay. So it's activation care. Okie dokie, NR is fine. Now, so I'm looking at this actually. So now I have x, so I can put x and x.len. So what does it say? What does it say? what's wrong now? Expected 3 arguments, find 4. Yeah, because that's I'm calling run, and run is yeah, run is this function. Okay, so I don't need to lower to the assembly at this stage, so I can do just that. I can use a slice and everything. Okay, mut. So expected slice of F32 found the vec. That's just a matter of adding a few stars maybe. Expected F32 find integer. Really? Run is here, so we have the prog, we have the constant, and we have expected F32 found integer of, yeah, of course. Okay. And yeah, same thing here. I can even put it right there. Okay, and so expect will be a clone of x, and I'm going to assert that expect and expect x are the same. Okay, cannot mutable. Okay. So what I'm going to do is, I think that if I'm testing in release mode, it will be faster because we will pay a bit more of compilation time, but the binary will be so much smaller that the transfer to the place where the Raspberry Pi is should be, I mean, it should compensate. And if it's too slow, we can still use QEMU to test locally on the big PC. And then if it's still too much of a bother, we can also move on my Apple laptop, which is a M1, so it can run this code natively. It's a bit long for my taste, to be honest. It's long. It's boring. So while it's doing this, what I want to do then is I will want to make this a macro, so I can just the macro argument will essentially be this guy, and so I can use this macro over and over with any implementation of the kernel that we are going to support. And so I can actually put it in the same, probably put it in the same macro as this one. And also I want to make it, I mean, for the NOP case, it's a bit silly, but I want to make it a prop test so that it will generate random inputs and find me bugs that I haven't dreamed of. Of course, we can't see anything. I think it will not copy it again. Yes. So only the generic activation have been run. That was expected. But why this do not run? That's a bit more surprising. It's in generic activation, so it's definitely there. Oh yeah, it's there actually. Okay. So our test is running and it's tested, but this is a Rust implementation, of course. So the test macro is in frame activation tests. So here we did some, let's say, end-to-end test with the actual functions. But now what we're going to do is we're going to make this, we're going to move it. I will make it a different macro just for, so that it's a bit clean. So that's frame level test, and this will be kernel test. And actually, I mean, it doesn't have to be split. It's just, yeah, just use less complication. So we will just split it like that with a new line. And so we want to test prop activation. So with the condition, with TI, with our kernel, and we want to test now nope. And so I need to define nope as a program. So where should I do this? Where should I do this? Maybe just there, actually. Oops. So in the same way as we define the useful activation in SRC, frame, activation, definitions. So these are interesting ones. I mean, they do something. We will define a couple of stupid ones. So nope will just do tone. And it doesn't require any constants. Let's import whatever is missing. Yes. Tone is uptone. Like this. Yes. Actually, we will have a couple of them, so I will do this to be able to use the short forms like this. Okay. Getting rid of this. Now I have my nope test, and here just need to make sure that it can find it. So create with a dollar frame activation tests with an S, nope. Why is it not happy? What's wrong? Doesn't like never expected the token. Okay, what was the expectation? Then it was okay, hidden. So let's make it a path. Is it still complaining? No, now it's fine. So we will test locally. We should have an extra run. Okay, so that doesn't work. Right. So what is the problem here? The problem is, so I had an ident. Yeah, I want to be able to call it as a function. Its ID. No, it was ident. Oh yeah, it's not happy with this call. So the other way is to say that, yes, I need to detail it so that I can write the prop test rules in a nice. I mean, I don't need to write it. That way it works. Yes. So I want to keep being able to detail that. So what I could do is I could, if I do this, it should work actually. Yes, let's try it like that. Unused import, really? Create frame activation. Ah yes, reference is hard-coded there. Starting to be cumbersome. So maybe I want to maybe I want to split yeah, to have two different cases. Another option is to, no, that won't work. Yeah, this will not work. It will not work because what I want to do is, I mean, if I want to do this, I can still do it, but I need to have in reference and in definitions, I need to add these new functions. So, and I will have more than a couple of them. Okay, is it a good idea? The other way would be to duplicate somehow this macro, so one still works with this path and the other just refers to test. And one other thing is we actually need this to also provide us somehow the reference implementation. Okay. Right, so I'm going to duplicate the macro. So this will be prop test activation end to end, and I'm going to do a prop act care as I wanted to do actually. So yeah, didn't work. Okay, E2E is for end to end because we're actually testing the actual function that we want to run. And so I'm going to duplicate that. Maybe later on I will find a way to merge them again, but for now I will have a prop unit. And so unit test will take, I guess, it will be about the same. And what I'm going to do is I'm going to do the reference. I'm going to add the reference, the validation for the test as an expression. So the idea is I want to write nope and x done x, x gives x. So that's my refer. So that has to be proct act unit. So the no function, the function will be to find in create frame activation test this time. And the reference, instead of being like this, will be, oh yeah, plus there are many things that I didn't like with this test. Okay, expected will be input dot iter is a tensor, so input as slice of ti. dot iter dot map x, I can use refer, I think, dot collect, and I need to make this into a tensor, so let expected equals tensor 0 of expected. So tensor 0 is a macro that build tensor 1 actually, vector, so tensor frank 1 from doesn't find it, so it's in tract linalg, no tract data, and then it's in tensor literal, maybe it's in the prelude actually, let's see. Okay, tensor 1 is fine. What's wrong here? Expected, yeah, I will need to make it a vector of ty. So over elements of type, okay. What if I'm doing this like that? So input a slice unwrap iter map, so this should be ty. Something weird. Let me try to do that. Let me type system with typing the function. So we have a function of x ty that gives ty, and it's equal no, that's not, I wanted this. No. I know I had this problem before and I fixed it. I just need to remember what it was. So a problem where closure is provided to but I know what it is. I'm providing a closure to the macro, and then the type system is lost. And so by just rewriting the type of the closure, maybe I can fix it. And that was in, I had to do this trick here. Function CAB, yes, so that's what I'm looking at. So I have this let refer equals, I'll put a 2 here, fn of it's typing, fn of ti to ti, and it's equals to refer. And now here let me call refer to I'm happy it was yoked, because I would have been really unhappy. Thanks anyway for helping, or not helping, but thanks. Refer to, yeah, oh yeah, it's because here I have a reference to the float, and my closure expects the float. Okay, so this bit is right. Next, expected, yeah, it's just a matter of that. Output fill. So there is a problem with this test actually, which is something I really don't like. It tests with only one value by repeating it all over the place. And so if we have a bug in our kernel that is location dependent, for instance, if we swap stuff around, we will not see it. So We will probably have to, I mean, I want to fix this. What else? Output field. So yes, now I don't need that anymore because the test was doing it differently. Actually, it was computing the value by calling the reference implementation and then repeating it, but I don't need to do that anymore. So I can directly compare. So the function will change input. So I need to do that before. Up, let's move it up. And we need to check that expected is close enough input. Okay. So now it's working. One thing I want to do is also I want to test that we are not returning an error. So let's assert r equals 0. Here we go. Because that's how I want to signal that we are calling a non-implemented operator if it happens. And so yes, I need to change the function prototype. Guess. I mean, there is another way to do this is to test it, not testing it there, but asserting in the run function, which might be nicer. Let's look at this activation. So if I'm going to the run function, the actual implementation is here. So I'm calling k run. And I can even return a result, but the run over slice with alignment was, yeah, that's a bit of code that we isolate last week. And so it's in src frame and element-wise helper. So yeah, the function is not expected to return anything. So I'm gonna assert here. So let's assert that r is 0. And I still have a problem because krun is not supposed to return anything. That's yes, this one. No, that's the wrong place to assert actually. It's the right place to assert. So first I need here to change. So that's the prototype of the C function, that we are calling. So this one definitely needs to be to be able to return an integer. And this C function is actually called here. So if I want to do the assert, this is where it should go. Okay, so let's get rid of this one. And there is one more I added somewhere. Yep. So let's leave it. Let's leave this one as it was before. It was fine. Okay. Feels kind of right now. So the question is, if I'm running the test on my PC, I should see the nope test. No, not that many. Test ACNOP, okay. And if I'm going to the Raspberry Pi, so I'm not sure which one is faster. And I'm not sure I plugged them in already. So I'm calling actamp, and actamp is in src frame activations. .rs actamp, are you here? Actamp, yes, you're there. My fingers are weird. And so when I'm defining such a kernel, I should also test them. So testing them will be how was the macro called already? The macro was in tests, frame activation tests. So we have prop act e2 end-to-end and prop act unit, but this one, so that's the one we want to call act tests. I'm getting rid of the frame here because we have all of them in one place. So act test, it will take the kernel, which is the condition first. So the condition, I think I have it in the macro. If not, I will need to add it. Yes, I will need to add it. So condition. So the condition is actually super useful here because it's the bit that says if we can actually run this test wherever we are running. So we will not run our half precision test on a machine which doesn't support half precision. So condition, we need, I forgot already, frame activation tests. So condition kernel, kernel expected as a type, so it will be it will be this as $func, I think. And we need the operating type, which is $ti. Okay, so only the generic stuff is run. This is expected because I started the compilation way before starting plugging in stuff. So, so the missing bit, is bioct. The missing bit is the condition. So I'm going to add it there, and it's an expression. And condition expression. Okay. So it's no longer act frame test, but act test. And this is in generic activations 97 act tests. Okay, what? This should not happen. Oh, the error is up there. Okay, I thought the error was this dude, but no, that's fine. So generic, not generic. Yes, I need to add the condition. But as I was saying before, if you were there, this, I mean, we are in this case, the vector single precision are always provided on ARMv8, so we don't need to do anything more than check, than putting true. But yeah, that's what we need to do to test the half precision, but not now. No function alignment bytes. Okay. This is surprising. So that's in frame. So that's yeah, frame activations. Tests. Output non-zero line TI. No function. So it looks like it's yeah, it looks like it's using the function name and not so the idea is what the macro does, the other one. Yeah, there are really a bunch of macros here. But what the macro does is it defines a function as sys plus the function name. I mean, no, but it's in a splitted module, and the function is called function. And then it defines this object and with. Okay, so I think it's just the trait, yes, and I had the answer just. Thank you, Rusty, for giving me the answer. I should have looked for it, and so here I can just, if I do this, I guess, and I will have the same problem with the other kernel down there. Okay, so that's a different one. Prop test. Usually this happens because, yes, I know why it happens. It happens because I'm calling, when I'm calling the act test, which is not there, it's in frame. A bit confusing, isn't it? When I'm calling the act test macro, I need to check that I'm in the test context with config test, because if I'm not, then I cannot use the test framework, and prop test is a test framework, so that's just it, I think. Looks better. So now we should see a bunch of tests failing. So because the end-to-end tests will fail, and we should see the no-op test run, because what we did actually works with no-op. Not at all. What did happen? Let's try again. It looks like a synchronization issue between the PC and the Raspberry Pi. Okay, that's more worrying. Uh-huh. The Raspberry Pi, is the Raspberry Pi dead? A good thing is it's just under my desk, so I can reboot it if it comes to this. Okay, gonna reboot the thing. This wasn't part of the plan. And let's try again, and if it's not working, I'm switching to the M1. Nope. Okay. That's fine. We'll manage. We'll manage. So let's evacuate pool. Try to fix this. Okay. So now I'm on the M1. So it's the same PC that I'm streaming from. So I hope it will be okay with the load. Cargo test. Huh. Damn. What's happening? Do I have... Let me check if I don't have another... No, I have nothing running on this PC right now. I've seen this before on this laptop. And it goes away after a while, but... okay. This is starting to be problematic if I have no machine that is working. Checking if the Raspberry Pi is back, but it doesn't look like it's back. So it might be several things because network configuration is also a bit complicated. That's not super nice. What? And I have no idea what generate this. Okay, that's something else. Okay, we'll go back to Tsar. At least we can do stuff here. What I can do, if the Raspberry Pi doesn't answer, I can still use Dingy to test with QEMU. So I'm going to use QEMU arc. Test. Okay, so we're running the test in emulated mode, but Okay, but it says what I said it would do. So something which is not great is we don't have activation in the test, so we're going to fix this. Because I want to know, I want to be able to filter the test, but basically all of them are failing, which is exactly what we were expecting. So tract linalg. I hope we are back on tracks. ARM64. So what I want to do is, so I said I want to add activation in the test path. So ARM64 SIMD, nope, that's going to be in frame. Actually, it's a bit weird. Why doesn't it put? Oh yes, because it's on the inclusion site. I mean, the macro is executed on ARM64 SIMD, and it puts everything right there. So we need to fix that. In tests, I'm gonna just add act test. So this will generate a mod test or mod act. Actually, it's act that I want. I don't care about test. Up. So now I should be able to filter. Okay, I broke everything. I broke everything. So what happened? It's so this is a type, so it's fine. So I guess no, that's fine too. A trait with a similar, so act tests. Consider importing this tract, but where? Where is the problem happening? The problem is happening. So I moved act. So that way it's working, and act test. So act test, it's this function, and it's called with types, so it shouldn't matter what I'm doing with them, because they should follow. Putting it back, entering again. So act test. So it's not found. It's happened in generic, and it also happened in my other thing, and it's doesn't make a lot of sense actually. It doesn't make a lot of sense because the types here should just be mapped. Okay. The thing is, I have act in the names here, so yeah, the big problem is not what I thought it was. The problem is I should have, because if I look at, for instance, if I look at all the F16 tests, which I'm not sure will be supported by QEMU, we will see. Yes, and there is also a catch somewhere. Okay, so we have generic MMM, then we have test generic, and then we have a bunch of stuff. So I guess I should try to reproduce that kind of thing. And what I want is I want I'm tempted to let it go for now because that's just macro stuff, and I've been teasing the assembly stuff for so long that I want to try and do some. So let's forget about this for now. Here, I mean, the problem is I'm still not seeing my tests actually. Because I only have the generic ones running here, and I'm on QEMU ARC64. So something not right is still happening. ARM64 SIMD. So I'm calling ActAmp with this stuff and with true here. Then this bounds to src frame activations.rs, and I get this stuff. So I'm calling act tests, and act tests are in src frame activation tests. So I'm getting these. So I'm going to test something stupid. Yeah, I can hardly start. I can hardly start writing assembly if the tests are not working at all. So test ARM64 SIMD foo. That's the one. Do I have other ones? Maybe it looks like I have other foo tests, but not great. So this one is working, but I need to be able to find these guys. So I need to be able to put a module around this stuff. Let me check, because yes, here I am in the same module. So I have the function which is actually the struct. I have the implementation of the type, and at the same level I have the act tests. So should I do something like that maybe? Am I in a paste? Yes, so I can do. Let's try something like this. Test func. Okay. Not one in scope. That one I expected, but I can fix it like that. Hopefully. And still don't get what I want. Okay, so I'm testing for foo. Yep. So I can test now. I should see nope. Yes, finally. So I have the test prefix, I have the name of my kernel, and I have my test. So now I can just test activations. Okay, and we are back there with all of the functions that are not working yet. Okay, finally some progress. So, and we can see that something that is not working is, yes, because our assembly always answers 0 and we are not using the return value, but now we can use the return value. So I can try this. ARMv8 activation. So instead of returning 0, I'm gonna return 1, and we should see, instead of this error which says it doesn't work, we should see the assert where we check the error status of the extensity function. Assertion failed, left 1, right 0. Okay, we're getting somewhere. So now we have the nope test, and we're going to make a second one. I want to make Relu to work. So what I'm going to do is there is a lot of ground to cover, but let's try it. So I'm going to add a test for max. Activations, tests. So if I want to test for max, I will have alpha, and it won't work. I'm not sure because alpha, I don't have it there. So I will need to, no, it's not going to work with this approach, unless I can. Oh yeah, maybe I can do this. Have alpha here too. Yes, and I'm going to do x. So let's try to make this work now. That's max const. So closure is expected to, yeah, so we need to, can no longer use this. I mean, we can, but we need to add all the params, the extra params here. Expected, yeah. So can I dispense with this? It would be nice. I hope I can. But so here I'm now taking x, and I'm calling refer of x and the params. Yeah, all the params. Let's try it like that. Nope. Yes. Okay. It's not complaining too badly, except it wants a type for x, but that maybe we can accommodate. I need to have a max const here. So max const will take max const, it will take a constant of t and put it there. Okay, it's good. And so here it needs to know what x is. seems happy. So max const will fail. Yes, max const is failing as well as no op. Why is no op failing now? That I didn't expect. Oh yes, because I'm returning 1. Yes, no, that's fine. So this can go. Okay, so let's try to write some assembly. Finally. So if I look at the new, where am I? Okay, new SRC frame activations. So the C function is here. So that's a function that my assembly must implement, and I'm gonna cut it, pasting it here to see it. Oops. Okay, so that's my function. Let's remove the extra stuff. So we get first a pointer on the operators, a pointer on the constants, a pointer that we're going to mute with all the values in the slice, and the number of elements on the slice, which is supposed to be a multiple of 32. So we need to iterate over this over len actually. So len will be in so that's how it works. So from now on, I mean starting there, x0 is x1 is constants, x2 is x's, and x3 is len of x's. So we need to do a loop that will run over the x's. So we will need a label. I'm using outer loop because there will be an inner loop on the constants. And so first of all, we are going to check that if len is null, then we need to just return, because we have nothing to do. So that's let's have a look. I don't remember how these things work. It's always the same thing. I mean, it needs a while to be to remember all the tricks. Okay, so CMP seems to be that the x3 with 0, and the jump is called branch in ARM64, and so branch if equal, that's back, and so in this case I'm going to return, and I'm going to do OK. That will do just this, and disable jump to return. So that's my happy path. If we do nothing, We jump to OK, we put a 0 in x0 because 0 contains ops, which is a pointer, so hopefully it's not null. And so we're putting a 0 and then jumping into the return stuff. So here we go to OK. Then we're going to do the outer loop, and so at the end of the outer loop we'll be removing sub from x3. I'm going to remove 32 because I can process 32 value at a time. So here there is a lot of stuff that we're going to do. I'm going to move x2 of not 32 but 32 times 4, so 128, because that's I'm moving 128 bytes down the slice. And I'm going to do this one with a comparison. I think this exists. Subs ARM64. Yes, this is right. And I'm going to look at an example to make sure that I get the test in the right direction. Subs. Okay, this one is, yeah, that's how it should be. I think this CMP is just redundant. Sub 32, and I can do branch if not equal. So if we're not at 0, then we jump to outer loop for processing the next 32 values. Okay. So that's this is our outer loop. So the loop that will process 32 bits at a 32 float at a time. Now we need to run over the operators. So to run over the operators, first I will need a pointer to the current operator that we are going to run. I cannot move x0 because every time I start the outer loop, I need to put it back at the first operation in the table. So I'm going to put in x5 x0. So x5 is PC, as in a pointer to the next instruction. It's often referred as PC in assembly. So now we have the inner loop. And the inner loop will do a lot of stuff like this, and ultimately it will move x5 of 4 bytes because our instructions are 4 bytes, and it will look at the next instruction, and if the next instruction is down, which is 0, then we get out of the loop, or else we do whatever the instruction commands us to do. So at the end of the loop, we will move x5 to the next instruction. So x5, I'm adding x5 plus 4, and I'm jumping back at inner loop in all cases. So that's B, no condition, to inner loop. So at the beginning of the loop, I have X file that points to the next instruction. So I can load that LDR, I think so, in X6. So this is the fetch. If we try to use CPU description language, so that's X6 is fetched instruction at X5. Okay. And so I'm going to start simple. So I'm going to do, because there are many ways from very naive to very complicated to do the jumping table, because here basically we have a switch case. Depending on the value we read in X6, we must jump to one place or the other in the code to do the actual content of the instruction. I'm going to start with something very simple. So I'm comparing X6 to 0, and if they're equal, I need to jump to end of inner loop. So this is what happens if we find the down operation in our program, because we must stop what we are doing and move to the next 32 slice. So in that case, we are going to land here. We are going to move X2 and X3, and depending on the result, we are going to start again. Okay? And if so, let's try to figure out what is a new number for max const. So max const is 1, 2, 3, 4, 5, 6, 7, 9, 10. Okay, 10. Well, yeah. And if we are following here, this means that we haven't found the instruction that we are supposed to do. So we are going to do unsupported. And so unsupported will be, for instance, there, unsupported. And it will make an error code of 1. And it will jump to return. Okay. So now let's try to figure out a couple more things, because the outer loop must also manage loading and storing the data. So here I need to load, so don't remember this is so there are like a dozen of ways to load things in ARM, in the vectors, but I mean, we're not going to worry too much about performance for now. So let's look. Okay, so what I want is something that will load to V, so LD1, that is LD1 like this. Yes. So inner loop, outer loop. So right here I'm loading to A. I'm going to load 8 full vectors, so ld1, and the syntax is v0 vo.4s, v1.4s, v2.4s, v3, and I'm loading this from the address in x2. Yep. And then, so I can only put 4 of them on one single call. So v4, v5, v6, v7, and they will be loaded with x2 plus 128. Is that correct? Each of these guys contains 4 float, so that's 4 times 4 equals 16 for each vector. And there are 4 of them, so it's not 128, it's 64. Doesn't feel correct. It feels, so this is 16 plus 32, so no, 64. Yeah, 64. Yeah, 64 bytes, not 64 bits. So yeah, it's. I think it's fine. So here we have loaded some. We have loaded the current 32 values, and at some point, end of inner loop. Here we need to do exactly the opposite to store them back into main memory. So if it was correct up there, it should be correct there. Then we're moving x2 of 128. Yeah, that's correct. 64 plus 64, that's 128. I'm going to try to be consistent with my use of, yes, and still there are more over there. Okay. All right, so the last bit that we still need to do is max const. I mean, there is not one single chance in the world that this works the first run, but let's try it. Let's try to be confident. So max const. So to do a max const, we'll have to call fmax, the fmax function. And so some of the ARMv8 vector function works with can work with scalar in the second part, but not fmax. So I will need first to put the constant in one of the vectors that we kept for housekeeping. So so where is the constant actually? So that's yep, there's something broken. Oh yeah, there's something broken because the instruction is one 32-bit integer, and the instruction code, the opcode, is only the first byte, if I remember correctly what we did last week. Activations. So no, it's okay. The first half. So the 16 bits give us the instructions. So we should not use X here in the hash table, in the switch case table. We need to use whatever. I mean, is there a way to refer to the first 16 bits of generic purpose register names? Okay, so we have X and W. So X are 64 bits, which are not what we want, and we have W's for the 32-bit equivalent, but it doesn't look like there is. There are some. Yeah. Okay. So we will need to do some bit manipulations. It's fine. So X is in axis. We have fetched the instruction. So we need to. I mean, we're doing a we're doing a virtual machine because we fetch. Now we need to decode. So we are going to and I think that's and we're going to end x in x7. We're going to end x6 with 0x f to get. Is that correct? I want to keep. I want to extract the I want to extract 16 bits. So nope, that's not what I need. I need this to extract 16 bits. Yeah. Okay, and then this is what I need to compare with the values. All right, and so now in max const, what I'm going to do is I'm going to do it. Yeah. Oh, okay. Let me check about this end thing because I'm not 100% sure. ARM64 instructions. I have a huge PDF that contains all of this somewhere. If I don't find it right away, I'm going to the PDF. The only problem is the PDF is absolutely huge. And it will take like half a minute to open, provided that I can find it again. Yes, it was there. Okay. What is that? Oh yeah, this is when I was trying to work before we get, I mean, on the laptop. Okay. So I will need to extract the constant. I will need to do a vdup of the constant on v. Let's say v23. No, v23. So the first housekeeping is v24. So what will happen is here we will load constant to v24. So we will load it in the first position of v24. Then we will duplicate this first v24 number over the four values of v24, and then we are going to do fmax of v0.4s, v0.4s, and v24.4s, and we need to do that 8 times. My shortcuts are not working, so I'm going to do it the hard way, the long way. Nearly there. Okay, and once this is done, I will just go back to. I need to go back here so that we add. Yeah. So we'll call this before or inner loop payload tone. And so here I can jump to inner loop payload down. So all of these need points, need dots. So it shouldn't be dots, it should be else, but for now we will put dots. Okay, so the only bit missing is this guy. So we need to extract. Is my PDF loaded somewhere on some screen? Yes. So advancing this, so alphabetical list. So I wanted to check AND, but that's correct. Perform a bitwise AND of register and an immediate and write the result to the destination register. So this AND will do an AND between this stuff and X6 and put it in X7, so I can check it against these values. So now I need to extract from the third byte of our constant of our operation. So I need to do right shift. So right shift is logical. So LD are loaders. So logical shift right by variable number of bits. So I want the immediate version by an immediate number of bits. Okay, so I'm shifting left, logical shift right. I'm going to put the result in X7 again because I'm done with it, and X6 by 16. No, by 16 bits. Okay, and then I need to once again mask it. So I'm going to mask X7. And this time it will be just 1 byte. Okay. And so this is the number of the constant I want to load. So I need to compute the address of the constant, or maybe not. Maybe I can load it in one go. LDR, let's see, if I do X7, I think I can do X7 plus 4 times. So no, it's not X7, it's X. The constants are in X1 plus 4 times X7. I'm not sure if this works or if there is a value to make it, a way to make it work. Maybe like that. I think I remember something like this. Let me check in my huge corpus of assembly. Not obvious from there. Oops. Nope, that's not what I want either. And okay, let's just try to compile it first. I think I have everything. I mean, some bit will not work, some bit will not compile, but I think, oh no, because yeah, I don't want to load in. No, this is wrong. Okay, so because I need to load in the vector registers. So in x7, I have the number of the constant. I'm going to left shift left this time x7 2 times. So this is multiply it by 4, and then I'm going to add x7 to x2, and this to x1, and this will give me the address of the constant that I want to load. And finally at this stage, I can load in v24s0, v24.s.0, whatever is at x7. All right, so I think I have everything, and I'm certain that it will not even compile, but let's see. Okay, it doesn't compile, so I have reti somewhere, so that's just a typo. vdup doesn't seem to exist, so how do we do a dup in ARM64? Okay, dup. What else? Expecting blah blah blah. Yes, that's syntax problem. Just right here, we need some braces around what we want to load. And the syntax is super weird because it's like this. Okay, segfault, nice. Do I want to start debugging this right now? Plus, it's gonna be complicated because of I mean, it would be super easy to debug on the Raspberry Pi, just logging in and running GDB. But if I cannot, I'm going to try again. But maybe that's gonna be it for tonight, and we have some debugging to do next time. Let's see if the Raspberry is back online. I'm not too sure about it. How can I do anything else? Because really the right way to figure this out is to use GDB or lldb or some debugger, which is so much easier when QEMU is not making it harder really. So I think it's gonna be it for tonight. We have a bit of assembly that doesn't work. It's a bit frustrating, but at least we've written some assembly. And next week we will just start right there with a nice debugging session, I guess. So I'm going to commit this, and hopefully next week we have a working solution.